Taking a look at practice question set number 9 that was due this morning. 4 questions on this practice question set. And of course, this is in preparation for quiz tomorrow, right? We always have a quiz the day after we check over practice question set. Question number 1 says Newton's law of universal gravitation has a mathematical relationship similar to the one developed by, this is a pretty easy question, right? Who would it be? This is Coulomb. This is A, right? Now, what do we call that relationship? Yep. Good, it's an inverse square relationship because the force is inversely related to the square of the distance. Now that's what they have in common. The relationship are both inverse square relationships. What's different about Coulomb's law versus Newton's law of universal gravitation? What's one thing that's different? Yeah?
One thing that's different is the numerator of the two, which is how one uses mass and the other uses
Okay.
charge.
So we're using different variables, of course, right? We're using different variables. But beyond that, kind of a little bit more generally, yeah? The magnitude, right? The magnitude of the electric force is going to be bigger than that of the gravitational force. And what else goes with that? The direction, right? The electric force is attractive or repulsive. It depends upon what type of charges we have. And of course, gravity is always going to be an attractive force. There's no way we can have a repulsive force there. Good. Question number 2. Which of the following graphs represents the relationship that Coulomb determined with between force and distance between two charged metal spheres? Force and distance. If I was plotting force versus charge, whether it be charge 1 or charge 2, what relationship would I get? That's a linear relationship, somebody said, right? It's going to look like this. So if the relationship between F and Q is linear, then it's certainly not linear between F and R, right? So we know that C is not the case. Which one is it? Is it A, B, or D? It's D. B can't be the case either, right? Because as R goes up, we know that F has to go down, and that's not the case with B here, right? It does end up being D. As R goes up, F goes down exponentially. F is equal to KQ1, Q2 over R squared. R goes up, F goes down, big time. All right, 3. Pretty straightforward question if we recognize a couple of things here. First thing we got to recognize, of course, is the charge of the alpha particle. It says on your data sheet that it's 2 plus 2e, and the charge of an electron is negative 1e. But the other thing we got to recognize, of course, is what is an e, the elementary charge? Well, it's 1.6 times 10 to the minus 19. So this is positive 3.2 times 10 to the minus 19 coulombs, and this is negative 1.6 times 10 to the minus 19 coulombs. Now we want to find the force here. We're going to say K Q1 Q2 over R squared. 8.99 times 10 to the 9. Times 3.2 times 10 to the minus 19 times, what comes next? Yep. Yep. Good. It's not negative 1.6, right? When we're plugging our numbers into Coulomb's law equation, we never plug the sign of the charge in there. It's only the magnitude. So 3.2 times 1.6, and then we divide that by 4 times 10 to the negative 10, and we got to make sure that we square that distance there. Okay, when we do that, we should get D 2.9 times 10 to the negative 9 newtons. And finally, number 4, Coulomb started with 2 identically charged spheres separated by distance r. The force between the spheres was F. If you change the separation to 2/3 r, then the force between the spheres would become what? Well, this is one of those questions that we did way back, not with Coulomb's law, but we did use the technique way back near the beginning of Unit 1. You guys remember what we called that technique? I called it variable value changing. The name of it's not really that important, right? Whether you can do it or not is the important thing. When we're doing variable value changing, we're changing the values of variables without knowing what the variables were to begin with. So we start off by writing out an equation. My force is equal to KQ1 Q2 over R squared. That's pretty clearly, I think, the relevant equation here since we're trying to find electric force. We're going to call this, though, my original force. Before I make any changes to it, this is what my force is. Now, if I had a value, I would write in that value right there. 25 newtons, write it in right there. I don't. So I'm just going to leave it as my original force, KQ1 Q2 over R squared. Now, my new force is also the constant times the charge over the distance squared, but this time we're going to replace the symbol for variable or variables with another symbol. K isn't changing. Q1 isn't changing because we didn't change the value of Q1 or Q2. But the distance we did. The distance was R. Now the distance is 2/3 R. So if my original force was KQ1 Q2 over R squared, my new force is KQ1 Q2 over 2/3 R squared. Now, notice what I just did. I put the 2/3 R in brackets. Why? Well, because I'm squaring not R. I'm squaring the distance. And the distance is not R. The distance is 2/3 R. So I've got to square everything, including the 2/3. Now let's simplify this a little bit. It becomes K times Q1 times Q2 over, well, let's square 2/3. It becomes 4 over 9 R squared. I want the brackets to disappear because I want to pull that number out front. Does that make sense? Now let's simplify that a little bit further. If I go KQ1 Q2 over 4 over 9, that's the same thing as doing what? Dividing by 4/9 is exactly the same thing as multiplying by the inverse of it, 9/4. So it becomes 9 over 4 times KQ1 Q2 over R squared. And we know what the value of KQ1 Q2 over R squared is. It's my original force. So it's 9 over 4 times the original force. My answer becomes D for that one. All right. Now, a couple more little things before we go into the computer lab to do our activity here. What I want to do right now is not go over the questions from worksheet number 7 that you had for homework last night, but rather just go and draw the free body diagrams for those. I asked you to solve all of question number 1. Okay, if I draw the free body diagrams for question number 1, A, B, C, and then take a quick look at D, then I think it'll be okay. If not, then I'll ask you to stick around on your schedule to help and ask me a couple questions on that, okay? And then I want to do one more example, and then I'll tell you about the activity that we're going to do, and then we'll head down to the computer lab. All right, so here we are, worksheet number 7. We want to draw the free body diagram for A, B, and C. We have 3 charges in a straight row. The first charge has a value of positive 5 times 10 to the negative 5. The second one is a charge of positive 5 times 10 to the negative 5. And the third one has a charge of negative 2.5 times 10 to the negative 5. My distance here, distance is 2.5 centimeters or 0.025 meters. And my distance between the second and third one is 0.020 meters. All right, for the first one, I want to find the net force on the first charge. So because of that, I'm going to draw a free body diagram for the first charge. Call this one A, call this one B, and call this one C. B applies a force on A, clearly. C also applies a force on A. That one's a little less clear because there's one of them in between. That doesn't matter. So both B and C both apply a force on A. Let's look at B first. Pretend C's not even there right now. If B applies a force on A, we know it's going to be a repulsive force because positive and positive repel each other. A is repelled from B. A goes away from B as a result of that force. I'm going to call that FBA, force of B on A. Now, we also know there's a force on B, right? The force of A on B, A pushes B to the right. Why am I not drawing that in right now? I'm looking for the force on A. I'm looking for the force on A, not on B. There is a force on B, but I don't really care what it is right now. I don't care what direction it is because I'm trying to find the force only on A. What about C and A? Pretend B's not there now. What about C and A? Is that attractive or repulsive? C on A. Positive and negative, they're going to attract each other. So A is attracted to C. A is pulled towards C. Now, I don't care if B's in the middle there. Pretend it's not there right now. A is attracted to C. Now, C is also attracted to A, right? But we don't really care about that because we're not trying to find that one. Once you've got the values of FCA and FBA, and you can do that fairly easily, right? Calculate those values, KQ1, Q2 over R squared. Then we got to add them up. But what do we got to be careful of when we add these two forces up? What's the big thing, Emma? Yeah, usually FCA is going to be positive and FBA would be negative there because it's acting to the left. One other thing you got to be careful of when you're calculating FCA, what are you going to make the value of R? The value of R, the separation distance between FC and A. Okay? Right, you got to add these two together, right? Because you need the total distance between C and A. All right? B says, find the force on the second charge, on the middle one. So we've got positive, positive, and negative again. The force of A on B. Is that attractive or repulsive? A on B. Shiva, is that attractive or repulsive? Those two positives. Yeah? So if it's repulsive, B is going to be pushed away from A. Right? Now, A is going to be pushed away from B, but I don't care right now because that's not what I'm trying to find. Now, what about C on B? Is that attractive or repulsive? August, is that attractive or repulsive between B and C? Yeah, because it's opposite charges attract, right? So B will be pulled towards C. B will be attracted towards C or pulled to the right. So both of those forces are to the right. We can calculate both of those values and then add them up. Both are positive. And then finally, we take a look at C. Once again, we got positive, positive, and negative. We're trying to find the force on C. Let's look at A first. Are A and C attractive or repulsive here? William, A and C attractive or repulsive? Yeah, because they're opposite charges. So C is going to be pulled towards A. I'll call that FAC. And Jamie, is B and C attractive or repulsive? Yeah, because they're opposite charges. Good. If it's attractive, then C is going to be pulled towards B. Now, B is going to be pulled towards C as well, right? A is going to be pulled towards C. I don't care. Right now, I don't care. Question C, I'm trying to find the force on the third charge. All right. Now, I am asked to find for the acceleration of charge 1 as well, the first charge. All I'm going to do there is say the force on the first charge divided by the mass of the first charge. And we're given the value there, 7.5 times 10 negative 2. So I can't remember what you get there, but that's a pretty easy question, right? Just make sure you use the correct mass, that's all, and the correct force, because we've got 3 masses and we've got 3 different forces here. Is that okay? Yep.
So when we add the forces together,
Yes, that's a good question. When we're plugging when we're plugging values into the equation for KQ1, Q2 over R squared, we do not plug signs of charges in. But when we're adding forces up, like for instance in question A, F net is equal to FBA plus FCA. Remember what we said? For us, negative means direction. That's why we left it out of the equation, because we don't want negative to mean a type of charge in an equation. We want it to mean direction. If it means direction, then we have to make sure BA is a negative value and FCA is a positive value. So absolutely. Okay, when you've got a negative that means direction, absolutely put it into the equation. Okay, when you got a negative that means the sign, then don't put it into the equation. Unless you're like averaging or something. Remember when we averaged, plus 5 and minus 5? Well, you have to include the negative then, right? But generally in a equation like this, you drop the sign of the charge, that is. Okay, I want to do one more example, and then I'll tell you about the activity that we're going to do in the computer lab today. This is example number 2. This is on the handout that I gave you yesterday. We got a question that's real similar to what we had for our example yesterday, except this time my third charge is not to the right of the second charge, but rather it's below the second charge. Numbers are all the same, just the position of it's a little bit different. Listen, when you look at this question, I'm pretty confident that many of you, maybe even most of you, could solve this question without my help. This is a Coulomb's law question where we have more than one force acting. So what do we do first? Yeah, go ahead, Joshua.
find the x and the y.
Even before that, even before we deal with x and y. Chase? Free body diagram. Draw a free body diagram. Okay, we know that A is a positive value, B is a positive value, and C is a negative value. Draw a free body diagram for sphere B, the middle one. Well, A and B are both positive, so they're going to do what? Attract or repel each other. What's it going to be? Repulsive. So that means that B is going to be pushed away from A. I'll call that FAB. Now, A is going to be pushed away from B as well, right? But I don't really care about that one because that's not what I'm trying to find right now. What about B and C? Kristen, are they going to attract or repel each other, B and C? They're going to attract because they're opposite charges. And as a result of that attraction, B will be pushed away from C or pulled towards C. Danny, pushed away from C or pulled towards C? Good, pulled towards C. So we're going to make that FCB downwards towards C. Well, you can calculate both of these forces. In fact, you may not realize this, but you already have. Because the numbers are the same as the example yesterday. If you look back to the example from yesterday, you actually have those numbers. But what do you do with them? Yesterday, you would have just added them together. Maybe one was positive, maybe one was negative, but you just added them together linearly. What do you think you're going to do here, Logan? Yeah, this is a free body diagram. We need to draw a vector diagram. And a vector diagram is going to look like this. FAB, whatever its value is. FCB, other way. FCB, whatever its value is. How are you going to find the net force acting on B? Let's do the Pythagorean theorem. Calculate the force using the Pythagorean theorem. And of course, the angle is going to be found by the inverse tan function of opposite over adjacent. Now, there's one more way that I could have added these together, but it's real similar to what Logan just told me to do. Yeah. So you could have drawn FCB first, and then FAB second. When you do that, you're going to get the exact same value for F. The exact same value for F, but theta will be different, right? If the first theta was, let's say, 40, what would the second theta be? Yep. Nope. That's the same answer somebody in the last class gave me, actually. It's funny. Hamish? 50, right? 90 minus 40 is 50. Good. I'm not sure off the top of my head what those angles are, but one's going to be the complement of the other, so 90 minus the other. You guys okay with that? We don't need to go through the math on that, do we? Are we okay? All right. Your homework on this stuff for tomorrow is your worksheet number 7, the worksheet that you were working on, question 3 and 4. That should go fairly quickly for you because really all you've got is a couple of those, 2 of those to do. So finish those up for tomorrow, please.